In the last part of this lecture, we're going to touch upon more advanced topics on the accurate modeling of catalytic surface reactions with the Kinetic Monte Carlo algorithm, and we will discuss sources of complexity that have to do with the structure of the material. For instance, complicated structures like this nanoparticle would have to be captured using some custom lattice structure. Then we can have complicated reactions which may involve several sites, more than 2 sites, for example. They may involve species that are multidentate, which bind to more than one site. And finally, we may have coverage effects, so lateral interactions between the species that are reacting, the molecules, the reactant molecules, and spectator species, which change the rate constant of the reaction. So in the first part of this, we're going to deal with these two, and then finally, we're going to discuss coverage effects in a bit more detail. So in this part, we're going to talk about the graph-theoretical Kinetic Monte Carlo approach, in which the lattice can be represented as a graph. So here is an example of a graph that captures the catalytic surface of a truncated octahedral nanoparticle. So in this nanoparticle, we have different site types, right? So we can represent these in our graph. So we have the top sites and the FCC sites of 111 facets. We have the top sites and the bridge sites of 100 facets. We can also explicitly represent the edge and corner sites of our nanoparticle. And of course, since we have the graph theoretical approach, we can have arbitrary connectivity of these sites to capture the geometry of the nanoparticle. So this is quite a flexible approach. It allows us to capture a vast range of catalytic surfaces and catalytic structures using this graph theoretical approach. Now, so this is one of the components in the graph theoretical approach. The second component or type of information that we need has to do with what kind of adsorbates are sitting on which sites on the surface. Now, if we have monodentate adsorbates that sit on one site type, things are quite easy. However, we would like to also capture multidentate adsorbates, like this configuration for carbon dioxide here, which is in this case a bidentate species. So in the graph theoretical approach, multidentate species are allowed and the orientation is explicitly captured. So we take into account the fact that this CO2 species can bind with the carbon subunit to one site and the oxygen subunit to the other site. So then we can explicitly capture the orientation on the lattice. So let's look into the lattice state representation in a bit more detail. This is an example of a bidentate adsorbate in which subunit 1 is occupying site 2, subunit 2 is occupying site 1. So as we mentioned earlier, we have our lattice, which represents the catalytic surface, and then we somehow need to provide the information about the occupancy of each one of the sites and also the orientation of the adsorbates. So here is how we do this. We introduce an array which has 3 columns. The first column is just a number, the entity number. It's basically just an integer that really labels the adsorbates on the surface. So, for example, site 1, which is this site here, is covered by entity 15. Site 2, which is this site here, is covered by entity 5, etc. Now, you will notice that in this case, where we have this bidentate adsorbate, AB, star star means that it occupies 2 sites. So in this case, we have 2 sites that are covered by the same entity. So the site numberings are shown here. So this is site 24, right? The rectangular site here, and this is site 31. So if we go into our state array, site 24 is covered by entity 31. Site 31 is also covered by entity 31, right? So this is entity 31. So this allows us to tell that this site and this site are both covered by the same entity. So this is the first column, the entity number. The second column of our array is the species number. So for empty sites, we use this concept of the vacant site kind of pseudo species. So the first site is empty, second site is empty, third, etc. So all of these sites have species number of 0, right? So vacant site pseudo species. Then the seventh site over here is occupied by species number 1. So the seventh site would be this site up here. Species number 1 is this A star species. Then the 18th site is occupied by the second species. So this is site 18 occupied by B star, etc. So this is how this works. And the third species is this A B star star. So sites 24 and 31, right? 24 and 31 are covered by species number 3, which is this AB bidentate species. So by this we have captured the entity and the species, but we don't know yet the orientation. So the orientation is captured by the third column, which gives us the dentate which occupies that particular site. So of course for monodentate species, like the empty site pseudospecies A, B here, we see that there is only one possibility, one valid value for the dentate. Dentate number 1, there is only one dentate. However, for the bidentate species here, which is sitting on sites 24 and 31, we see that site 24 is occupied by the first dentate, site 31 is occupied by the second dentate. This state is different than the state where site 24 would be occupied by the second dentate, site 31 by the first. So this last column, the dentate column, is the one that captures the orientation of bidentate or multidentate species. Now we have the inverse mapping of that to allow fast computation. So if somebody asks me, okay, here is entity 7, what type of species is this? Where is it sitting on the lattice? Then I have the inverse mapping of the array that I showed earlier, the lattice state array. So then immediately I would go here. So this array is sorted by entity number. I would go to the 7th entry. So this is for the 7th entity. And I would say, okay, this is species number 2, and it's sitting on site 18. What about, let's say, entity 31, which is the bidentate? Entity 31 is species number 3, right? This A, B, star, star, and it occupies sites 24 and 31. So this is useful. It's useful to have this inverse mapping because when we execute a reaction event, we would like to know the entities that participate in that reaction event so that we can remove them from the lattice and then add new entities, the product species, onto the lattice in the final state of that reaction. So quick lookup and quick update operations are facilitated by having the reverse mapping of the state array, which is exactly this array here, this array over here. Now, we have talked about the representation of the catalytic surface as a lattice and also the state, but what about the elementary events that change the state of the lattice? So the elementary events are also captured as graphs. So here is an example, CO oxidation. So this is one side of the pattern, the graph pattern that corresponds to the elementary event. This is covered by oxygen. The other site is covered by CO. So this is the initial state of the elementary event, and the final state would be CO2, the bidentate species that sits with this subunit on site 1, this subunit on site 2. So if we have a collection of such connected graphs with an initial and the final state which correspond to elementary events, so if we have a collection of these, then we can use this subgraph isomorphism solver to map the possible possible reactions onto patterns on the lattice. So solving the subgraph isomorphism problem will allow us to identify all the possible elementary steps that may happen on the lattice and map them to lattice processes. So let's look at this here. We would like to detect patterns in which an oxygen and a CO are occupying neighboring sites. So here are the possibilities: 1, 2, 3, 4 patterns. So any of these could be a valid reaction in the next Kinetic Monte Carlo step. And after we have identified these lattice processes, we generate a random time for each one of these to happen sometime in the future. And it happened here that this was the one with the smallest time. So this was the most imminent event that gave rise to a CO2 bidentate species on the surface. So this is how the Kinetic Monte Carlo algorithm can progress by identifying all the possible elementary steps using the subgraph isomorphism solver, and then generating random times for these and simulating the most imminent event, as we mentioned in the previous part of the lecture, at every step, every iteration of the main Kinetic Monte Carlo loop. Now, solving the subgraph isomorphism problem is or can be computationally expensive, because what we are essentially doing is that we're creating permutations of n sub sites out of NL lattice sites. So NL is the total number of lattice sites, n sub is the number of sites that appear in the pattern. So if we want to detect this pattern, for example, then we would have to take combinations of 3 out of all of these sites, 32 sites in this case, and then check the occupancy and the connectivity to see if they match the pattern that we want to detect. So this way we would eventually be able to find all the possible instances of this pattern on the lattice. Now, of course, as you may imagine, right, creating permutations is a very computationally expensive problem. Checking the permutation is not as complicated. We just have to check the connectivity and the occupancies. But going through all the possible permutations can be quite computationally expensive. So there are some optimizations that we have implemented in the graph theoretical KMC. So we check the permutations while constructing. We use a variation of the subgraph isomorphism algorithm by Ullman. This was suggested back in the 70s. So we have implemented a variation of this algorithm in the graph theoretical Kinetic Monte Carlo. And we also, instead of considering all the possible lattices, lattice sites, we consider only sites within a certain distance from an entity. So if we know, for example, that we have a NO molecule here is our reaction, NO plus CO give us nitrogen datum on the surface and CO2. So if we know that this NO is sitting on these sites, then it suffices to check in the neighborhood of this NO whether there is a CO, and we really don't have to check the entire set of lattice sites. So we can check this neighborhood over here. So we see that there is indeed a CO, but in this case the site types don't match. The square sites are the sites in which on which NO is sitting, then the circular site is the one on which CO is sitting. So this is not a valid pattern, but we can continue the search, and we can try this one here. So this NO is sitting in the correct site types. Then we can check the neighborhood of this and try to find a CO adsorbate which is sitting on a square site, and indeed this is a valid pattern. So then the subgraph isomorphism solver would return this as a valid instance of this pattern, and of course then we can create the process in our process queue, create a random number for the time that is going to occur, etc. So this way we achieve the localized pattern search, which is much more efficient than going through all the possible permutations of all the lattice sites that we have. So then this event is detected, and then it can happen. So we end up with a nitrogen adatom on the surface and a CO2 in the gas phase that the algorithm counts. So given a lattice state, each lattice process, each instance of an elementary event on the lattice is fully specified by the type of that elementary step, whether it's CO adsorption, CO desorption, nitrogen adatom diffusion to another site, etc., or reaction between CO and NO, for example. So that's the type of the elementary step, and we need some more information, the site mapping. So the site mapping basically says that the first site of the pattern maps to the 23rd site of the lattice, the second site of the pattern maps to the 24th site of the lattice, for instance. This way, we know that process 1, for example, is elementary step 1. This may denote CO adsorption, for instance, and it happens at site 4. So site 4 would be empty in the initial state and then occupied by CO in the final state. Process 2 may be a CO oxidation process, for instance, right? So elementary step 2 would point to the CO oxidation event, and this would involve sites 4 and 6. And by the definition of the elementary step, then we would know that, for instance, site 5 here would be occupied by CO, site 6 by an oxygen adatom in the initial state, and in the final state these sites would be empty, and a CO2 would have been elicited to the gas phase. So this list, this array here, or data structure, gives us, for each lattice process, it gives us the elementary step and also the sites that are involved in this process. So this information can also be supplemented or expressed in a slightly different way that also involves the entities. So in this array, which we call the participation array, we ask the question, which processes does entity EI participate in? So the first entity, which would be an adsorbate that sits on some in some lattice site, would participate in 5 processes, and these would be processes 34, 12, 65, etc. So these numbers would point to processes here. So then we would know that entity 1 participates to this reaction, which is this elementary step on these sites, to this other reaction, this other elementary step on other sites, etc. So this is how we structure the information about reactions, right? So process, what is the elementary step of the process and which sites does it happen in, and then with respect to the entity, so which processes does this entity participate to. So in terms of bookkeeping, a minimal graph theoretical kinetic Monte Carlo simulation would encode the information about the the state of the KMC simulation in these arrays that we show here. So we have the lattice state, first of all, which gives us the entity, species, and dentate for each one of the sites. We have the inverse mapping of that. This way we can go back and forth, right, between the state of each one of the sites and then the entities, so the adsorbates or the empty sites, so we can know which sites are occupied by these entities using this array here. Then we have this participation array, which tells us which processes, which elementary processes does each one of these entities participate to. And then finally, we have the information about each one of the lattice processes, including the elementary step that this process is, and also the sites where it takes place. So this basically is giving us everything we need to know in order to be able to update the state of the Kinetic Monte Carlo simulation and also do sampling. Now, what about the selection of the next event that is supposed to happen within a Kinetic Monte Carlo simulation? So we have mentioned quite a few times by now that every time we detect a reaction on the lattice, we have to create a random time, right, an exponentially distributed random number that tells us when this reaction is going to happen. And then once we have a complete list of all the possible reaction events, we find the minimum out of them and we execute the corresponding process, lattice process, at that time. So in order to do that, namely select the next event to happen, we can do this with the brute force data structure. We can put all these generated times in an array and then try to find the minimum out of all of these. But this would be quite computationally expensive because every time we would have to go through the entire array, and this would be an operation that would have a linearly increasing cost, linearly increasing with respect to the size of that array. So the question is whether we can do something better, faster, more efficient. And there is a data structure that allows us to do this. This is called the heap structure, which is a partially ordered binary tree, like the one that is shown here. So at the top node of this binary tree, we always have the most imminent event. So in this case, the most imminent event would be lattice process number 4, and the time that this is supposed to happen is 0.02 units of time. Now, in the partially ordered binary tree, there is a priority rule, so each node has priority over all its children nodes. So this element here has priority, namely smaller time than all of these elements below that. This node has priority compared to all of these elements below that, etc. This has priority over this has priority over these elements. However, we don't know, so if we look into this node here and that node here, we don't know anything about the priority between these two because there is no parent-child relationship between these two. Right, so we know that this has lower priority than this, but if we are to compare this and this, we cannot make any statement. And that's why you can see that in the same level, you have the 8th process having time 0.11, but then the second process having a higher time than this, or the 7th process having a lower time than this. What we can state for sure is that these two processes have higher times than this, so lower priority than this, which is the parent of these two children nodes. So the priority, of course, is determined by the event's execution time. So lower execution times mean higher priority. And of course, the top node has the highest priority of all of them. Now, in this heap structure, the insert, update, and remove operations reorder the tree so that the heap priority is always satisfied. And these operations in general take time, which is scaling as log n. N is the number of processes that we store in the binary tree. So this log n is much, much faster than the n, the order n operation that we would have if we were to try to find the minimum in an unsorted vector. And that's why this heap structure is more efficient in general. And of course, for large kinetic Monte Carlo calculations with hundreds or thousands of processes, it is much preferred to use the heap structure as opposed to the linear vector, the unsorted vector. As I mentioned a moment ago, the next KMC event, the imminent KMC event, is always at the top. So we basically find the minimum in constant time, and these insert, update, and remove operations are the costly operations that are performed in log n time. So efficient kinetic Monte Carlo algorithms would implement heap structures for the queue of processes to be executed. And there would be, of course, operations, subroutines that deal with the addition, removal, or update of a process, which would result in automatic sorting. So let's look at some of these operations, starting with the heap removal operation. So here is our tree with the nodes corresponding to the possible processes that may happen, and we have the time over here. So the process that is imminent here is the fourth process with time 0.02. So let's say that this process just occurred. It was executed by the Kinetic Monte Carlo algorithm. So this is now removed, and we have to fill in the hole that remains. So we have to choose one of the two children to take the place of the fourth process that was just removed. So obviously out of these two, this is the one that has higher priority because it has the smaller time between the two, right? 0.06, smaller than 0.08. So this is promoted now. Then we repeat. So out of these, this has the priority. So it takes this place. Then out of these, this has the priority, so it takes this place. And finally, since we would like to have as much as possible complete levels, we're going to take this process here, this node, and reattach it over there. Finally, we note that now the numbering of processes has a hole, right? So process number 4 just occurred, so our process numbers go from go like 1, 2, 3, 4 is missing, and then we have 5, 6, etc. So we would like to relabel the 10th process to be the 4th process because we want to have consecutive numbers in our labeling. So this 10 is going to be renamed to 4. So this completes the heap removal operation. And let's move on to discuss the heap addition operation. So now let's say that we detected another feasible process on the lattice. So we're going to have to add a 10th process in our binary tree. So here is the 10th process. And let's say that this one is very, very fast or very frequent. It has a very high KTST, rate constant. So now that we removed it, we see that we have violated the priority rules of the binary heap. So we would have to swap these two elements. And then we have to swap again because these are now violating the heap property. And then we have to swap again because of the same reason. So now here is the top node. It's the process that we just found. And this would be the most imminent one that should be executed in the next iteration of the main kinetic Monte Carlo loop. We will finally talk about coverage effects.